Hi, everyone. My name is Sarah. I'm a PhD student at MIT, and this is joint work with Andrew Ilyas, who's presenting next, and Aleksander. Okay, so I'm going to start off with a very obvious statement, which is that data-driven algorithms are built on data, begging the question, where does the data come? And in many settings, the data comes from humans, right? So in recommendation, which is going to be the focus of the next talk, the platform issues recommendations to a user. The user then interacts with those recommendations, and those interactions become the training data on which the platform then regenerates the future recommendations. Okay, so typically to make the system work, we assume that user behavior is what we call exogenous. So specifically what I mean by that is that if a platform issues the same recommendation, the user would respond to it the same way, no matter what platform it's on or what algorithm is used to generate it. So in other words, the way that you interact is based on the content alone. But in practice, we know that users can actually learn about their system, they can adapt to their system, and they can adapt in a specific way in that they strategize. So for example, they can respond to the same recommendation differently based off of the algorithm or system that generated it. And I want to argue that strategization is common, right? So on social media, for example, we might have a user who believes that the platform pays too much attention to their clicks. And because they believe that the platform pays too much attention to their clicks, they might avoid clicking on content that they actually like, or they might end up searching for those links in private mode. And just as a little preview, we ran a little user study. This is part of the next presentation. And we had users say things like, sometimes I may like a song, but not thumbs up the song because I don't want my feed filled with similar artists or videos. I avoid reading certain news stories on Google News because I know I will be bombarded with similar articles. Instead, I switch to an untracked browser to read the story. And even some users who have interesting behaviors like having many accounts. I have many YouTube accounts, so my algorithm does not pick up on a YouTube link that my friend sends me to watch. And I believe this strategization actually extends beyond just recommendation settings. So you can imagine an Uber driver who learns that Uber represents their preferences as unimodal, and as a result uses Uber for some types of rides, like longer rides, and uses Lyft for other rides. Okay, so this is the motivation of this work, and the question that we're trying to answer is, what are the implications of this type of user strategization? So as our main contributions, we present a model. The model is basically a repeated two-player game. The platform is going to issue what we call propositions, i.e. recommendations in this last setting. And the user then interacts with those propositions, and they repeatedly interact in this way. We're going to define how this model can capture user strategization. We're going to show that this type of strategic behavior can actually help the platform in the short term, but that actually hurts the platform in the long term because it corrupts and manipulates the data. And the last thing we're going to do is connect this to trustworthy algorithm design, where the punchline there is essentially that, if you have this exogeneity assumption, you don't have to pay attention too much to what the users think, to how much they trust your system. But when you remove this exogeneity assumption, when you account for strategic behavior, trustworthy design becomes a key important concept. Okay, any questions so far? All right, so there's a lot of related work here. As you might be able to pick up on from the language that I'm using, this is very closely related to mechanism design and strategic behavior, and we draw a lot of similar concepts from there. And we'll talk about how the concepts that we draw on and the concepts that might differ in some of the later parts of the talk. The way that we construct our model is highly related to both repeated alternating games and also various literature on myopic and non-myopic users. Including some work by some folks here, I think I saw in the audience. And lastly, closer to this sort of like econ CS area, we also are presenting work that's pretty similar to, draws on some of the same themes as strategic classification, but there are very important and subtle differences, and I'm happy to talk about that if you're interested. And of course, this related work slide is not exhaustive. Okay, so what's the model that we're using? We have a bunch of time steps. At each time step T, the platform is going to generate the propositions Z T, for example, recommendations, ride requests, diagnoses. The user is then going to respond with some behavior, and their behavior is going to be conditioned on that proposition that they see, ZT, and it's going to be drawn according to some distribution, Q condition. And then, of course, the platform and the user collects some payoffs, V for the platform, U for the user. All right, so we're going to take the perspective of the platform for a second. What does the platform do? To generate propositions, the platform is going to try to learn a model of the user behavior, and then based on that model of user behavior, issue recommendations that, or issue propositions that they think the user will engage with in the way the platform wants. So to do this, the platform has this class of user models, and it's going to consider user models such as Q hat inside this class. Okay, so in reality, we have something that probably looks like this. The platform has this class of models, call it capital Q hat, that consists of these various user models, little q hat I. And user's actual behavior is somewhere outside of this class, so the platform is misspecified in some way. And we're going to denote that by this little q. What the platform does is it maintains a belief about the user's behavior Q. And it's going to update this belief at every time step based on the evidence that it observes. So, i.e., ZT, the proposition, and the behavior in response, BT. And for this work, we're just going to assume that the way that the platform updates this belief is with a Bayesian update. So the belief, which is given by mu at time step t plus 1, is going to be updated according to the belief at the last time step plus times how likely it is that this user model predicts the behavior that was actually observed. Okay. The last key concept here is what I call the algorithm, and this is denoted by little p. And the algorithm basically maps a belief to a proposition. So the platform is going to generate a proposition ZT according to some distribution P that's based off of their belief about the user mu t. So for example, if I, as a platform, believe that you like cat videos, that's my belief. How I behave is kind of separate from that. So how I use that belief with other propositions, whether I use it to give you more cat videos or whether or not I use it to say, hey, I think that means that you like animal videos in general, so let me give you some more animal videos, that is governed by this algorithm P. Okay, so in summary, we have this sort of repeated alternating game where you have a platform issuing proposition ZT, the user responds with some behavior B, T, and then they collect payoffs. But I'm missing this sort of key component to this narrative here, which is that before the game starts, the way that the user decides on their behavior Q might actually depend on the platform. So we're going to just model this as this basically Stackelberg game that's followed by this repeated alternating play, where before the game, the platform declares their algorithm or their system, P, which is how the recommendation algorithm works, and Q hat, which is the set of user models, so how it characterizes users. And then the platform decides on their Q, which might depend on P and Q hat. So this is sort of how this becomes non-exogenous. Any questions? Okay. All right, so then how do we model user strategization? Just recall our goal is to capture behavior like I might like a song, but not thumbs of it because I don't want my feed filled with similar artists. Or I might or have many YouTube accounts and my algorithm does not pick up on a YouTube link my friend sends me in this sort of like repeated game. And effectively, what is happening is that users know that their current behaviors, their current actions are affecting their downstream outcomes. They anticipate that and they adapt accordingly. Okay, so this is going to lead us to define two like stereotypical users that we call the naive user and the strategic user. So the naive user is going to behave as if there is no personalization algorithm. So there's no future consequences to their action. And we can capture that like this. We're going to denote that by this QBR, Q best response. And effectively what the user is doing is they're choosing the action that maximizes their immediate payoff. Okay, then we're going to define this strategic user who is very different from the naive user. And actually, this is the infinity strategic user, but I'm just going to drop that prefix for now. And the way that the infinity strategic user behaves is they choose an action that benefits them in the long term. So it's going to maximize some equilibrium payoff. And so it looks something like this, and we call it Q star. Effectively, what this is on the right-hand side, this is just the worst case limiting expected payoff under some choice of behavior Q and the game dynamics. Meaning, like, if I played Q, this is my expected payoff as T goes to infinity under my choice of Q, and I already know the platform is using this algorithm P and the set of user models Q hat. Now, what I'm going to do as a strategic user is I'm going to pick my behavior that maximizes that limiting payoff. Okay. All right. So we have this definition here, but is this actually something that we can characterize? Is it something that we can work with and manipulate? And to do this, we basically borrow from some literature. So just to contextualize it, the key point of the strategic user is that we need to characterize how they behave in the infinite time limit. And to do that, we borrow results from misspecified learning literature, Sponda and Puzo, Boren, Freudenberg, and Frick et al. Here at Yale. And the general theme of this type of work is that you have this potentially misspecified Bayesian agent. This is the platform in our case. They're interacting with and learning from their environment. You can think of the environment actually as the user in this case. And their goal is to understand the limiting beliefs of that agent, and then to kind of use that to draw some conclusions. Okay, so the key primitive is this limiting behavior. And I skipped over a lot of technical details here. Happy to discuss further if needed, but I think the most important thing is actually this sort of like intuition, this geometric intuition. So the main theorem that we're drawing from is on the bottom here. And it basically says that support of the platform's belief mu t converges as t goes to infinity to this globally stable set that we denote by S infinity. And S infinity, importantly, depends on P, the platform's algorithm, Q hat, the platform set of user models, and Q, the user's behavior. Okay, so geometrically, the intuition is as follows. We're back in this setting where you have the user models given by this orange polygon, Q hat. The platform starts with some initial belief, mu naught, and so that's going to be this orange dot in the middle here. And then as play goes on, and the user behavior is given by that blue dot, and as play goes on, the platform updates its belief. And what this theorem basically says is that the platform's belief converges to what is known as a globally stable belief. In this case, I'm just doing this sort of, not the set, but this as belief, that is actually closest to Q in this KL sense. So this information theoretic sense. And so importantly, I just want to emphasize on the right here that this globally stable set, S infinity, depends on what the platform chooses as its algorithm and as its recommendation setting. So it depends on P and it depends on Q hat. So if the platform actually shifted its set of user models to this pink set, Q hat prime, what it converges to as T goes to infinity is also going to change, even if the user's behavior does not change. Okay, any questions? Great. So given this tooling, how do we actually characterize the naive user and the strategic user? Let's start with the naive user. And again, for just geometric intuition, this is an oversimplified graphic where along the sort of horizontal axis here, we're just projecting user payoffs. So we're just assuming user payoffs actually only depend on this horizontal axis. And so the user's best payoff is actually over here on the right. And that's why that actually corresponds to the user's best response behavior. Okay, so QBR is the user's best response behavior, and that's their behavior if they don't really care about the algorithm, they don't pay attention to future payoffs. And in this image here, we're starting again with the platform's initial belief, which is given by this gray dot. And what actually happens is that if the user plays their best response or their naive behavior, QBR, the platform converges to this Q hat BR mu infinity, which is the platform's globally stable belief. And because the platform is misspecified, what ends up happening is that the user's payoff is actually quite low. Does that make sense? Okay, so the strategic user is actually mindful of this. And what they do is they would adapt their behavior QBR to some other behavior Q star. That taking into account this sort of misspecification is going to get them a better payoff in the long term. And in the paper, we have some cost that is put on the user for actually adopting this behavior. So it's sort of the distance between QBR and Q star. Okay. All right, so what are the consequences of such strategic behavior? These are some of the high-level key results that we show in our paper. The first is that user strategization can actually help the platform. So when the platform's payoffs and the user's payoff are sufficiently well aligned and the platform is misspecified, then strategization can actually help the platform learn better about the user, because the user is kind of cognizant of the fact that the platform is limited in a way. And so it can actually help the platform and increase the platform's payoff. So it's good for the platform in the short term, and that's sort of a very intuitive result. The second is also pretty intuitive. It sort of says that this is good for the platform in the short term, but it's actually bad for the platform in the long term, especially if the platform wants to consider other settings beyond what it's already seen. So specifically, if a platform collects data under one algorithm, its estimate of its payoff under a different algorithm can be arbitrarily bad for strategic users. So this sort of intuition is very obvious, but I think the part that was a little trickier was to show that you can be arbitrarily close to your past algorithm and still get arbitrarily bad estimates. So meaning that it's like very non-smooth. Some intuition here is that the platform can't disentangle behavior in response to content from behavior in response to the algorithm. And so it sort of struggles there. Okay. The last result, rushing a little because of time, is that the platform's payoff can decrease when it expands its model family if the user is strategic. And this is kind of an interesting result because this goes beyond our normal intuition when we have exogenous systems, or the exogeneity assumption, meaning that, typically in machine learning, we assume that if we expand the model class, we're only helping ourselves and helping our estimation. And this theorem says that if the user is strategic, actually, when you expand your model family, unexpected things can happen, and you actually can get a lower payoff. Okay, and so the paper, we have more general results, or the formal versions of these results, and we also provide a simple illustrating example of each one. Okay, so what should we do about it? This is where we come to trustworthy algorithms, and we give this definition that is actually closely aligned with some past literature. And it says that a platform is kappa trustworthy if the user is not incentivized to strategize and her payoff without strategization is at least kappa. So the user not being incentivized to strategize kind of intuitively maps to the user trust that the platform looks out for their platform-related interests, so the user does not have to do so themselves. This is kind of similar to concepts in market design and mechanism design. And the second is that the user payoff is sufficiently high, meaning that trustworthiness is not about just strategy proveness, which is element number one, but it's also that the payoff needs to be good enough. This sort of echoes individual rationality. The counterexample that motivates this second element is that if I'm a platform and I show you constantly bad content and you never engage with content, that is actually a strategy proof system, but that is definitely not something that we would consider trustworthy. Okay, so I'm just gonna stop here because I think I have 1 minute left. This is summary of results, but I'll just put up this slide and take any questions. Thank you very much.